Hi, we are demonstrating the experiment of coordinated nodding 2D Lidar for 3D range measurement. As you can see in the front, the sensor has two parts. The top part is the Lidar and bottom part is the servo that effectively provides the nodding effect. To calibrate the sensor, we used a corner-shaped object that has depth variation along its height. Now I'll run the experiment. We have used ROS to implement it, and the visualization tool of ROS, that's RVs, has been used to view the reconstruction. As you can see, the shape of the object is reconstructed accurately. The reason behind, as I said, choosing the object was the depth variation. Therefore, unless the pitch of the sensor is not calibrated well, that means the laser beams will have different pitch as the sensor nods. Unless we compensate for the pitch angle error of each laser beam accurately, the reconstruction cannot appear correct. Now, from this experimental results, we can validate that the setup has been calibrated accurately. Thank you. In this video, we demonstrate the ego motion experiment for the paper titled Coordinated Nodding of a 2D Lidar for 3D range measurements. The objective of this experiment is to scan a scene in front of the nodding 2D Lidar while mounted on a mobile robot. For ego motion, we let the robot move forward and backward with constant speed. We observe that as the robot approaches close to the scene, the field of view of the sensor shrinks due to the constant nodding angle limits of the servo. We also observe that although the nodding angles of the servo are adapted on the fly, the perceived point cloud of the scene appears to have bias towards the middle and lower portion of the scene. This is caused due to the constant nodding speed of the servo. Therefore, we designed a velocity controller for the nodding servo such that as the robot moves towards the scene, the nodding speed increases along with the nodding angle limits. The opposite happens when the robot moves backward. This produces a point cloud which is very close to the uniformly distributed one. Thank you.